All right, everybody, welcome back. We are now in our next video. In this section, we're going to be talking about optimizing EIGRP. When you deploy EIGRP into an enterprise environment, it is best to optimize the protocol to make it as efficient as possible. Now, the optimization options that we have with EIGRP, not quite as extensive as what you might see when you're running OSPF, because EIGRP inherently is a flat network design. But there are some things that you can do to make EIGRP operate more efficiently. Two of the major optimization techniques that you can employ are summarization and stub routing features, which allows us to do what we call query scoping. Now, you could also do traffic engineering. You could do equal cost and unequal cost multipath routing. There's other things that you could actually do to include or to have additional enhancements to EIGRP. But in this section here, we're going to talk about specifically those two behaviors: implementing EIGRP stub configurations to limit the scope of our EIGRP query range. That's going to make EIGRP more scalable. It's going to have fewer complications with regard to reconvergence if networks go down or networks are not available. And then secondarily, we're going to talk about summarization, right? By using summarization, we can reduce the size of our routing tables and optimize the exchange of routing information between the peers in the network. Also, to use all available redundant links, we support load balancing in EIGRP. We know that EIGRP by default already supports eCMP, which most IGP protocols do. That is equal cost multipath routing. But EIGRP can also do unequal metric load balancing by making use or taking advantage of the variance option and then using that in conjunction with maximum paths. So implementing these functions and these features can make the protocol operate more efficiently. In addition, we can implement some security with the EIGRP by ensuring that routing protocol authentication is enabled. That's a step that we can take to ensure that the routers are configured so that we have improved network security. And we do that by simply implementing neighbor authentication, which is going to be based on either predefined key chains with various key IDs and key strings, or key passwords that we simply implement as part of the authentication configuration process. So in this section, we're going to focus on what is an EIGRP query. We're going to talk about how stub routing can be used to reduce the number of queries when EIGRP goes into an active state, meaning that we lost our successor route. We did not have any feasible successors. So for that reason, we need to query our neighbors to see if we have a loop-free alternate path available to us. We're going to talk about what happens when we're stuck in query for too long, what we call stuck in active. And what is the issue with stuck in active? How do we deal with that? What are some of the legacy methods that we use to deal with that, as well as the modern methods? And then we're going to talk about summary routes, right? What is the impact of the query scope if we use summary routes, and how can we lessen the impact of the query scope by utilizing summary routes? We're going to wrap up the lesson by talking about load balancing. What are my load balancing options with EIGRP? And then finally, we'll finish the entire section by talking about applying authentication to EIGRP. So let's go ahead and get started in section 2.2. So certainly one of the first things that we need to talk about with regard to optimizing EIGRP is what is the effect of a query in an EIGRP domain. We obviously rely on neighbors to receive routing information and reachability information to the prefix destinations that we're trying to reach within our topology. And we already talked about in our previous introduction to EIGRP, we talked about the concept of a successor and a feasible successor. We talked about the concept of feasibility condition, what the impact of having a feasible successor is, when we lose our successor path, and so on. But we're going to kind of review that here in this particular case. In this section here, we talk about what is a query. So let's say in this particular case, to the left of this router, not just one network, but maybe we have potentially hundreds and hundreds of networks to the left of that router. Maybe that's our HQ site, and that's where all of our corporate networks exist. And router 1 is then connected to maybe a WAN location, router 2, and then we've got some branch locations in router 3 and router 4, and so on. Now, by definition, these routers to the right of router 1 are what we refer to as stub routers, not in the context of EIGRP, but in the context of general routing capabilities, right? A stub router is, in essence, a router that only has one way in and one way out. So, in other words, there's no way that router 5 would ever consider going anywhere else but router 3 to reach the 192.168.14.0 subnet. So for that reason, we can treat router 2, router 3, router 4, router 5 differently than we normally would in an EIGRP topology, because there is only a unique path to reach each destination from those particular stub routers. This is one of the conditions that we can apply to EIGRP that provides us the ability of limiting the scope of queries, and then also in turn limiting what the router advertises upstream to its peers by using something called an EIGRP stub routing feature. Now, what happens if router 1 loses connectivity to the 14.0 subnet? If router 1 didn't have a feasible successor, that route will go into an active state, and then that router will then send a query to its peer. That's what the orange line represents in this particular case. We'll send a query to my peer saying, I lost my primary path, I did not have a feasible successor, do you still have a path to reach the 14.0 subnet? Now, router 2 should actually say, nope, I don't have a path, because router 2 can only get to the 14.0 subnet through router 1. But let's say for some reason that didn't happen. That query is then going to propagate downstream to router 3 and router 4. Subsequently, the query will propagate down to router 5, 6, 7, and 8. Traditionally, though, here's the problem. If, let's say, for some reason router 5 did not respond to the query, router 3 is not allowed to respond to router 2 until all of its active queries are resolved, and router 2 is not allowed to respond to router 1 until all of its active queries are resolved. In this particular case, that's not a problem, right? Because the gray line indicates that we've gotten replies from everybody indicating that the path is no longer available. All right? Now, this process should only take, I don't know, a couple milliseconds maybe some microseconds, depending on the size and the scope of the network. But there really is no reason for router 1 to query router 2 in this particular case, because router 2 only gets to those prefixes from router 1. All right, so just as a quick reference here, queries are sent when a route is lost and we do not have a feasible successor. And by the way, those queries are sent to all of my neighbors, all of my peers. The queries themselves are sent to all the neighboring routers on all the interfaces except where the original successor was. Obviously, the original path is gone. That's the whole reason we've gone into an active state. There's no reason to query the original router because we already know that that path disappeared from that router. That's what triggered the whole process in the first place. All right, if the neighbors have lost their route information, they answer the query and they stop the query from propagating from that point forward. And ideally, that's what router 2 should do in this particular case, right? Router 2 should respond to router 1 and say, you know what, I don't have a route to that destination. But if that doesn't occur, then the queries are going to get propagated to the rest of the neighbors. Now, when the route is actually lost, the router sends that query packet to all the neighbors on all the interfaces. There is, again, that split horizon rule concept that says never advertise or never request route information from the original source. But the query itself is really used to identify if there's another alternate path to the destination. So in this example, we see I wouldn't say an enormous number of queries, but certainly you can see how this could be expanded to a large enterprise environment where we would see a great number of queries that get sent throughout the entire EIGRP domain. And that's because that 14.0 route on router 1 was lost. Router 1 sends the query, router 2 propagates that query because it doesn't have any information about the lost route, and that query ends up cascading to all of the neighbors, and then each query requires a particular reply. All right. I don't know that you would actually ever see this in real time. It would be very difficult to capture. But if you look at the topology database, and you just happen to look at the topology database when this query process is taking place, you'll see an actual active entry in that topology database. A P indicates that the route is passive, which means we're not trying to converge. We've already converged the route, we've already picked our successor, and we're basically routing to this particular destination. An A indicates that the route is in an active query process. We can see that we have no successors. The original feasible distance was 409,600. The Q indicates that we're in the query process. We see one reply, and then we have a remaining reply from 172.16.1.1, and we can see a little r indicating reply status, meaning that we're waiting for that reply. We're still within the window of opportunity for the reply to come. Now there's a timer that's involved in this process, a 90-second timer and then a 180-second timer. We'll talk about that in a little bit, okay? But overall, the query process itself, not very efficient. We send a lot of queries. The query has to be followed by a reply. And again, depending on the scope of your domain and how large the domain is, this query could propagate for a very, very long time. Well, not a huge amount of time, but certainly for minutes, which in networking terms is kind of an eternity. So we can either use route summarization, we can use EIGRP stub routing to optimize how the query process takes place. So let's talk about real briefly what a stub router is, and then we'll get into the discussion of stub routing in our discovery, and we'll take a look at how this stub routing feature works. All right. So router 5, 6, 7, and 8, we'll say in this particular case would be configured as stubs. In reality, router 3 and 4 should be configured as stubs, as well as router 2, because there's really no reason to query those routers for any information that's lost upstream. The only way that those routers get to that destination is through the upstream router. So the stability of our enterprise network design really depends on how we effectively design the query scope or the query domain in the network. And there's two ways that we can simply eliminate the need for queries. One is to use stub routing features. The other, which we'll talk about later on in this section, is to use route summarization. So when we're configuring EIGRP stub routing, it's going to improve our network stability. It's going to reduce the need for router resource and resource utilization, reducing CPU cycles and saving up bandwidth and as far as convergence goes. And it's basically going to simplify the remote router configuration. A secondary kind of side effect, if you will, or at least a component of configuring stub routing is that we can also identify what types of routes we're going to advertise upstream to the neighboring router upstream. Not only that we're not going to be queried, but we can also restrict the amount of information that we share with our upstream neighbors. All right, we'll talk more about that as we get into the discovery and so on. So it reduces the overall complexity of our topology. It simplifies the configuration, especially if we have a physical topology that looks like a hub and spoke topology, and we would simply enable the stub routing feature on those spoke routers, even if we have dual-homed remote routers as spokes, right? Because we still don't want to query spoke routers to identify routes that might be lost in the corporate network or at the hub. All right. We can also, identify what types of routes get advertised back to the corporate hub by identifying the type of stub router that we want to implement. So we don't actually have to configure route filtering. We don't have to concern ourselves with whether or not those remote routers are going to become what we call transit routers in our particular topology. All right. So another concern, though, with the query process, especially if you have a particularly large query domain, is what happens if we get stuck. When we go stuck inactive, that means that a query was sent to our destinations or to our peers, but for some reason or another, whatever that reason might be, maybe the router is too busy, maybe there's a lot of congestion, but for some reason we don't get a reply. Now, traditionally, when we send a query out, the router has to receive a reply to all of its queries before it can respond upstream. So router 3 has 2 active queries to router 5 and router 6. If router 5 for some reason cannot reply to router 3's query, then router 3 cannot reply to router 2, and subsequently router 2 cannot reply to router 1. And that would be obviously a big concern. If that happens for 180 seconds or 3 minutes, that's when we move into what we call a stuck inactive state. Stuck inactive, or SIA, or stuck inactive state. Traditionally, and this is not the way it works today, but traditionally this was a very bad thing. So let's say router 2 sent a query to 3 and 4. Router 4 got its queries sent down to 7 and 8 and got its replies and sent its reply to 2. But router 3 is kind of sitting out here waiting for router 5 to respond to its original query. Well, if router 3 doesn't get a reply from router 5, router 3 can't reply to router 2, and router 2 can't reply to router 1. As timers go, the 3-minute timer is going, which is the kind of the stuck inactive timer state, that 3-minute timer is going to expire or get reached between router 1 and router 2 before it gets reached between any other peer, because our router 1 was the very first router that initiated the first query. And look what happens traditionally if I go into a stuck inactive state, meaning that I haven't received a reply within 3 minutes. I reset the neighbor relationship. So router 1 would actually literally reset the neighbor relationship to router 2, and then that would, of course, move its way down the chain. Router 2 would reset its relationship with 3 and 4, and so on. All right. Now, what are some of the common reasons that we might see a lost reply, even though we still have an adjacency? Routers might not have enough CPU. They might not have enough memory. Maybe there's some kind of strange unidirectional traffic flow, or we don't have full duplex communication. It's a very rare scenario, but there could be a scenario where the reply, the query was sent, but for some reason the reply was lost. And again, if I don't receive a reply, we start to wonder if that neighbor is even healthy anymore. All right, you would actually get a dual level 3 message, syslog message, that says stuck inactive. Well, that was kind of a pretty aggressive approach to managing this stuck inactive process. So what they decided to do is, in newer versions of EIGRP, is they added a secondary query process called a stuck inactive query process. So basically what happens in this case is, let's say again the same scenario, router 3 is not able to reply to router 2. Router 1 typically would reset the relationship with router 2 after 3 minutes. But rather than doing that, we wait for 90 seconds. And router 1 will send a stuck inactive query message after 90 seconds, half of the timer that we would typically see for the original kind of defined stuck inactive process, saying, hey, you haven't responded to my query in 90 seconds. Rather than wait another 90 seconds and simply reset the relationship, I'm going to send you a special neighbor-bound stuck inactive query, and you can reply to that stuck inactive query directly without the downstream neighbor having to reply to you. So it's kind of like a little health check to say, okay, look, we're in active state. I'm waiting for some sort of reply. I haven't gotten it. Is the problem with you? And if you respond with a stuck inactive reply, I know that the problem is downstream, and I don't have to reset my adjacency with you. I need to maybe have you do the same thing. So router 2 would send a stuck inactive query to router 3. Now, if router 3 can't respond to an original query, it's likely that router 3 can also not respond to a stuck inactive query. And that's where after 90 seconds, this relationship would get reset. Router 2, because it's no longer waiting for any information from a downstream peer, can reply to the original query that router 1 sent, and we're back to converging. I mean, 90 seconds is still a long time if you think about it, but it's better than 3 minutes, and it's also better than resetting adjacencies that didn't have to be reset in the first place. All right. So again, we send out that stuck inactive query and get that stuck inactive reply. That happens after half of the time, where the active timer is halfway through its cycle after 90 seconds. And that just allows the neighboring router to respond with that stuck inactive reply to confirm to that upstream router that it's still searching for a replacement route, but it's not the problem for not sending that particular reply. Okay? Now, another way that we can actually shrink the query domain, probably I would say even a better way, a more recommended approach, would be to do EIGRP summaries. Okay? A summary route is a supernet. It's basically a summary of a large number of prefixes. And in the discovery, we'll actually see how to calculate summary routes. We're actually going to do those calculations as part of our discovery. But a summarization is basically taking a block of contiguous network addresses. This particular summary is not a great summary, but we're in essence summarizing these prefixes here, the 12 prefix and the 18 prefix, into a /16. So if for some reason the 12 subnet goes down, the gateway router doesn't really know that 12 subnet has disappeared because it was part of the summary. And as long as the summary route's being advertised, there's no reason to do a recalculation from the gateway's perspective. So we can use summarization to limit the query scope and obviously reduce the size of our routing databases, our topology tables, but we can also use this to limit our query scoping and improve convergence. If I receive a EIGRP query for a particular prefix, which by the way is described in the routing table by a summary, I immediately get a response with a reply message. So in this particular case, they're talking about it from the other perspective. HQ loses this WAN link. We presumably assume that this WAN link falls within the scope of the summary. HQ is going to send a query for that specific prefix. Gateway is going to reply with, yeah, I still have a route to /16. It goes to you. And HQ will then resolve that query process. All right, but in order for us to have effective route summarization, one of the most important concepts is that we need to make sure we have an accurate subnet plan that considers route summarization to start with. We have a little bit more flexibility with EIGRP because we can summarize arbitrarily at any point in the network, unlike OSPF where you can only summarize on the ABRs or the ASBRs. But in EIGRP, we can summarize at any point in the network in any direction. But it still does require us to have contiguous, clean blocks of addresses. Not knowing what these WAN links are, I could assume that they're within kind of a similar scope as the 12 or the 18 networks that you see here. We don't know that, but that would be the ideal plan, right? We have a /24, we have an 18/24. I could actually summarize the 12 subnet. I couldn't summarize it up to 18 directly because that would be 6 networks, actually 7 if 12 is inclusive. And you could do a block of 8, but you can't do a block of 8 starting at 12. You can only do a block of 8 starting at 8. The block size that you're creating has to be evenly divisible by the network number that you're starting with, and that's basically how the binary math works out. So I would have to do a block of 32 here starting at 0, but that would be better certainly than a whole block of 16 bits here. I could do a block of just 32 addresses in the third octet, assuming those WAN links fall within that scope. But it does require careful planning to accommodate summarization. You have to assign subnets in large blocks to one part of your topology so that you have those nice contiguous blocks that allow you to, that provide you the ability to do that particular summarization effectively, okay? Now we will talk about this in more detail in our next discovery, which we're going to go into here next, discovery number 3. We're going to take a look at configuring EIGRP stub routing, route summarization, default routing, and we're going to look at these in detail because there's a lot more to know about stub routing than just its configuration. We didn't talk about stub summary, stub connected, stub static, the stub redistributed and so on, stub receive only. We also didn't look at how we can actually calculate summary routes. But we'll get into that in the discovery, and we'll go into it in quite a bit of detail throughout the discovery. So we'll see you guys in a minute. All right, we're moving into discovery number 3. We're going to talk about in this discovery what we talked about in our lecture portion, which is basically how do I make EIGRP more efficient? How do I make it more efficient? What routers would I configure as stubs? Where would I apply summarization? Where could I apply default routing, and so on? So just looking at the topology, which routers do you think we would apply as stubs in this particular case? BR1, BR2, and the distribution router, right? Makes sense. Those routers are kind of stub routers anyway. There's only one way in and one way out. Maybe the distribution router we don't, because we have 2 different serial links, which means we do have an alternate path to reach a destination. But certainly BR1 and BR2 we would configure as stubs. So let's take a look at what we're going to be doing in this discovery. We're going to learn how to configure and verify stub routing, both for classic mode for IPv4 and IPv6. We're also going to configure EIGRP summaries for v4 and v6, and we're going to announce a default route so that we have full connectivity to the internet cloud. We do not have the option in EIGRP for default information originate, like we do with OSPF and RIP. So we have 2 ways that we can insert a default route into EIGRP. We can redistribute a connected or static route. In this case, it would be static because it's default. Or we can do a default network. I prefer to use the redistribute static option because it's a lot cleaner, but we could potentially use the default network option as well. We'll talk about what that is obviously later on as we move through the discovery here. All right, all the devices have their basic configuration. HQ is configured in named mode. BR1 and BR2 are classic, and distribution router is in named mode. Just to give us an idea of how it might differ, right, between the different configurations where we would apply these different configurations. All right, so we're going to enable stub routing on BR1 and BR2. That makes sense. Those routers only have one way in and one way out. We're going to configure a summary on our distribution router for all those prefixes that we have on the router itself. Let me go down here. So these loopbacks, we're probably going to be summarizing those particular loopbacks there. And then we're going to announce a default route from HQ, which is the one that's connected to the internet. And we're going to do this for both v4 and v6, which really there's no difference between the two. All the devices have their basic configurations in place. The routers are pre-configured with EIGRP. These are the specific interfaces. Again, Ethernet 1.0, Ethernet 1.0, Serial 2.0, Serial 2.1, Ethernet 1.0. All right. Just to keep that in mind, those are the interfaces that we're dealing with. On this side, Ethernet 1.1, Ethernet 1.2, Serial 2.0, Serial 2.1. Okay. Here's our device information with all of our IP addresses. We don't need to look at that. So task 1, enable the stub routing feature on BR1 and BR2 for IPv4 and IPv6. So let's go ahead and go into HQ. Let's make sure that we have all of our routes. That's the first step. So we're going to do a show IP route EIGRP. And we should see that we have all of the destination prefixes. We have the 96, the 98, and the 100. Those are those prefixes coming from the distribution router. We have the 1.0, which is the loopback. 2.0 is a loopback, I believe. Let me look at the topology diagram. Yep. 1.0 and 2.0 loopback on this router. And then 4.1, 5.1, and 6.1 are loopbacks on the branch 2 router. So we should see those as well. There's the 4, there's the 5, and there's the 6. We don't see the links in between because those are connected networks to HQ. So they're not going to show up as EIGRP routes. They're going to simply show up as connected routes on our HQ router. All right. All right. So we're just doing some basic verification to make sure we have our routes. We'll do the same thing for a V6, show IPv6 route, EIGRP, and we should see the similar concept here. There's the loopback, the 2 loopbacks on BR1. Here's the 3 loopbacks on BR2, and here are those external networks on the distribution router. All right. Notice they're coming over serial 20. These are coming over Ethernet 1.2, and then these 2 routes are coming over Ethernet 1.1. All right, so we do have full convergence. We have all of our routes in our routing table. That's always good to check, by the way, especially if you're going to be doing summaries. Before you decide to configure a summary, make sure that the routes that you're trying to summarize actually exist. Because then the summary is just not going to be accurate. It's not going to reflect the appropriate topology. So step 1, we're going to go ahead and do a debug terse. Remember, the terse option gets rid of the hello packets. And we're going to shut down Ethernet 1.2 on our HQ router. So let's go to our branch 1 router. And we're going to do our debug on our branch 1 router. Debug EIGRP packet terse. Again, that's just so we're not debugging hello packets. And then I'm going to go into my HQ router and I'm going to shut down Ethernet 1/2. Now, if I look at the diagram here, 1/2 is the link that goes to branch 2. Not branch 1, but branch 2. Which means HQ is going to lose these networks. And I'm actually going to do a Wireshark capture on this Ethernet 1.1 link to branch 1 as well. Because I want to show you what the queries look like. And we should see the replies as well and the acknowledgments, just like we normally would expect to see. All right. But I want to show you what it looks like from the perspective of the actual prefix that's being queried. There's a delay value that gets set in the query process that indicates that the route is basically dead, doesn't exist anymore. Let's filter out some of these, not selected, and apply filter and not selected. There we go. Now we're just getting our EIGRP datagrams. And actually, let's get rid of the hellos as well. I'm going to do opcode, apply filter, and not selected to get rid of the hellos. All right. Doesn't look like we're getting much at this point, but that's true because we don't have any activity on the network. All right. We got our debug running. We've got our Wireshark running. Now I'm going to go into Ethernet 1.2, and I'm going to shut down that interface. All right. Which means now I should see my queries and replies. All right, we're seeing some ICMPv6 stuff. Let me get rid of that. Apply filter and not selected. So query reply, query reply, query reply. All right. Now, we're not getting the acknowledgments. And the reason we're not getting the acknowledgments is because the opcode for acknowledgement and hello is the same. So I would have to remove that opcode of 5 in order to see the ACKs, but we'll assume the ACKs are going through. So we're seeing 2 sets of queries and 2 sets of replies, one for IPv6, one for IPv4. Interestingly enough, notice where the query is going for IPv6. FF02:A, which is the multicast address for EIGRP, and for IPv4, 224.0.0.10. Look at what's listed in the query. And by the way, it's coming from our HQ router. These are all the prefixes that were lost. The actual physical link between the 2 routers, the 101 link, which is this link right here, the 101, and then all these 3 links here were lost. So we can see specifically in the query, these are the routes that I'm querying for. And then I can also see inside the metrics that they specify a bandwidth and a delay. The bandwidth is a maximum bandwidth, and the delay is set to infinity, which basically means, hey, I've lost my route to this destination. We've poisoned the route, basically. All right. Our v4 query is pretty much going to look exactly the same. In fact, it looks identical outside of the, well, actually, we're still using the wide metrics in this case as well. So we see the delay is infinity. The bandwidth is not the maximum bandwidth, but we can see the delay of infinity, which is indicating that the route is no longer valid. We might be looking at the wrong, yeah, this one is the one with the same bandwidth. All right, so basically the HQ router is sending out a multicast packet to its peers saying I lost the route. If I look at the reply, which comes directly from router 2, BR2, we can see that the reply is stating, because basically this router should tell me I can't get to those prefixes, right? The reply is stating I can't get there. And by the way, the hop count is 1 because I came through you to get there. And if you look at the next hop, the next hop is listed as : because the route is poisoned. So basically, this is the reply stating I can't get there, and the component of the reply that tells the receiving router that the network is unreachable is this delay of infinity. Does that make sense? So that's the basic query, and they wanted us to do the debug because they wanted you to see that the router received a query. Received a query on Ethernet 1.0, sent an acknowledgement with a sequence number, and then built the reply, sent the reply with a specific sequence number, and then so on. So that's why they wanted us to run the debug. I'm just going to do an undebug all, turn that off, to see that process take place. Okay? Note that the debug command will produce a substantial amount of output when Ethernet is shut down. You should see a total of 2 queries that are received by BR1 and 2 acknowledgments that are sent by BR1. You should also see 2 replies. That's interesting because we didn't see that in Wireshark. I saw 1 query and 1 reply. I guess they're talking about the 2 being V6 and V4, which would make sense because we're not debugging IPv4 or IPv6. We did a debug just for the whole EIGRP process. So that's why we're seeing the multiple queries and the multiple replies, 1 for each protocol stack. All right. When the link between HQ and BR2 is shut down, HQ is going to query all of its neighbors for an alternate path to the BR2 networks, but BR1 is a spoke router. It's a stub router. It should never be queried if a remote network fails because it doesn't have a way of getting to those remote networks other than through HQ. So I think you guys understand in general the need to have a stub configuration. Let's go ahead and bring that interface back up on HQ. All right. Which one? In the book? Which page? Yeah, re-enable Ethernet 00. Oh yeah, the interface numbers in the book don't match because these are built based on the Cisco Viral Labs. We don't have those interface numbers, so usually, most of the time, it's the first number is a 1 for us. So whenever you see a 00, it should be a 10. Oh, was 01? Oh, yeah, that is definitely a typo then. Yep. So I see what you're saying. It's not the fact that the first number is wrong, it's the fact that the second number is wrong. Yeah. I'll make sure to fix that. Okay. Now, stub feature is really easy to implement. Basically, you just go into your EIGRP process and make the router a stub. But there's another component to stub configuration that's outside of the scope of limiting the queries. When you configure a stub router, you have 5 different options for setting the stub configuration. You can say stub connected, stub summary, stub static, stub redistribute, stub receive only. So not only does the stub feature limit other routers' ability to query you, it also defines what you advertise to your peers, what goes out of your EIGRP process. So it's a very, very interesting concept. And people always ask me, when would I use one of these particular features? And it is very specific to your environment. There is no rule to say you should always use connected, or you should always use summary, or you should always use static. It really depends on what you're trying to accomplish in your environment. But you do need to understand the impact that each of these is going to have. And I'm going to demonstrate all of them as part of our discussion here. If you were to, for example, do stub receive only. Let's say I went into my topology here and I did stub receive only on BR2. Obviously, that means HQ could no longer query BR2 because it's a stub. But it also means that BR2 is never going to advertise any EIGRP routes to HQ. And again, you might say, well, why would I want to do that? I want HQ to know about these prefixes. Maybe it's a specific scenario where maybe you have some static routing on HQ that points to BR2. Or maybe you want to limit the reachability of HQ people to getting to these prefixes. It's just a very specific use case scenario that you would decide to use maybe receive only or connected or summary or whatever. All right. But I'm going to demonstrate them so you can see the effect of implementing those different options. Even if the discovery doesn't go through all of them, I will go through all of them to show you what the overall effect is. Okay. So I'm not sure what they're going to have us do, but we'll take a look. All right. All right. So because we're going to demonstrate all these, I'm not going to read the information here. I'm going to actually demonstrate what each of these does. And you can combine these as well. You can do connected and summary. You can do static and redistribute. There's all kinds of ones you can do. But I'm going to show you what each of these do for us, and I'll demonstrate them. I don't know how much detail they go into the discovery on it, but I want to make sure that we go into quite a bit of detail. So we're doing this on branch 1, and I'm going to go into my branch 1 router. Remember, we're running, if I do a show run section router, on branch 1, we are running classic mode, not named mode. Okay, so I'm going to go config T, router EIGRP 10, EIGRP stub. And IPv6 router EIGRP 20, EIGRP stub. That's it. That's literally what I do to make a router a stub router. Now, what's interesting about this is I'm still getting my captures. Let me go ahead and take out my filter for my hellos. Should take it out. Oh well, we'll just clear it. All right. So if I look at my hello packets now, one of the things that you should see in the hello as part of the configuration, I believe it's in the hello, it should be in the hello, is the indication that this is a stub router. Let me make sure I'm going the right direction. I'm looking for router 2 to router 10. And I should, yeah, right here, peer stub information. So notice here, and by the way, this is a bug in Wireshark, but you do see that I am now advertising stub information to my peer. This is coming from router 2, the branch 2 router going over to HQ. It says I'm a stub, and then it tells me what kind of stub I am. Now, by default, if you don't specify a specific stub option, connected and summary are turned on by default. I've noticed this for many years. For some reason, and I'm not sure why, I think it's just the way Wireshark is interpreting the bits. Redistributed, it shows that it's turned on here, but it's actually not. If I go to my HQ router and I do show IP EIGRP neighbor detail, if I spell it right, you can see that this router is connected in summary. So even though Wireshark is showing redistributed as one of the options, it's not. The default, without specifying any option, is connected in summary. So what does that actually mean? Number one, it means that HQ can no longer query BR1, right? Because BR1 is now advertising itself as a stub. But it also limits the routes that are being sent to HQ. If I do a show IP EIGRP topology, this route here would be right here. This route here would be advertised because it's connected and it's part of EIGRP. This route would be advertised, and so on. Basically, any summary route that's being generated by this branch router and any connected route that's part of EIGRP would be advertised. So I'm going to demonstrate something here. Let's say I create a loopback interface and I give it an IP address of 5.5.5.5, 255.255.255.255. And I do a show run pipe, well, let's just do router. And I go into router EIGRP10 and I say redistribute connected subnets. Well, redistribute connected. I don't need the subnets keyword because that's automatic. And I go into router, IPv6 router, EIGRP20, redistribute connected. So if I do a show IP EIGRP topology, that 5.5.5.5 network is now part of EIGRP. You guys don't have to do this. I'm just demonstrating what the stub feature is doing here. So that 5.5.5.5 network is now part of the EIGRP process. But HQ is not receiving that route because it is, well, it is receiving it. Why is it receiving it? It shouldn't be receiving it because it is redistributed. Connected and summary should only be included. And by the way, when we say connected, we mean connected routes that are running EI. Oh, I know why. I think I know why. Show run section router. I'll bet they got lazy on their network statements. No, they didn't. They've got specific network statements. Let me try something else. Router EIGRP10, EIGRP stub connected. I want to see, it's still coming in, show IP EIGRP neighbor detail. Only connected routes should be coming in, and we're suppressing queries. That's interesting. That's very interesting. Let me try one more thing. IP route 1.1.1.1, 255, or sorry, 1.1.1.0, 255, 255, 255.0, 5.5.5.5. 5.5.5.6. Do show IP route. I'm very curious now because we did see in the Wireshark capture that redistributed was turned on. And I always thought that that was a Wireshark issue. But now I'm wondering if it's not a Wireshark issue. But let's see. Where's my static route? Not there. I guess I can't point it to a loopback. Let me do this. Take that out. Oh, it's a, did I do it as a /32? I did it as a /32. Was it loopback 5? IP address 5.5.5.5, 255.255.255.0. Now let's go back and add our route. Do show IP route. There's my static route. Okay. So if I go to router EIGRP 10 and I do redistribute static, show IP EIGRP topology, redistribute connected, and then I should see the 111 redistribute static. So now the question is, does the 1 show up here? The 1 does not. So I'm very curious if this might actually be a GNS3 thing and Wireshark is actually interpreting the bits correctly. Because in Wireshark, it is indicating that redistributed is turned on, which means redistributed routes would be allowed to go out. But the reason I did the static is because static routes are not allowed to go out. Redistribute static is turned off. You see what I'm saying? This helps because it gives you the idea of turning these flags on or off, changes basically what's allowed to go out of the router. See what I'm saying? So if I come back into my branch router and I go into my EIGRP process and I say EIGRP stub, connected summary static, then I should see the 1 route coming into HQ now, which we do. So I'm now kind of jumping around a little bit. I'm going to go back and explain what's happening here, but the reason why I did that is because the 5 network should not show up. By default, and I believe now, I always thought it was a Wireshark thing, but I think now it's actually a GNS3 thing, or at least the IOSV, virtual iOS thing. If I do connected and summary, redistributed routes should not go out. Only summary routes and only connected routes that are part of the EIGRP should be advertised out, period. And I had seen that before where that flag was turned on, that redistributed flag was set, but I never tested it. I just assumed it was just a Wireshark problem. But because I did add that redistributed route and it went out, Wireshark's reading the bits correctly. EIGRP is not reading the bits correctly. Because if you look at the actual show IP EIGRP neighbor detail, connected static and summary are here, but redistributed is not. See what I'm saying? So that must be a bug. I hate to blame GNS3, but clearly it's not working the way it should. That redistributed route should not come to me because it's not part of the stub configuration. So you can now imagine, well, here's a good test. What if I did receive only? What if I did EIGRP stub receive only? What should go out in this particular case? EIGRP stub receive only. What should go out in this case? Nothing, right? Nothing should go out. And if I do my detail, I should see receive only peers advertising no routes, right? Which means that 1.1.1.0 network should not go out and the 555 network should not go out. So that appears to work. Interesting. What if I did EIGRP stub connected? I think we already did that one. What if I did EIGRP stub redistributed? The 5 network should show up. The 1 network should not, because it's redistributed statically. It's a static route. That might show up because it's still redistributed. But the loopback should not be advertised. The connected loopback should not be advertised. So if I look at my detail, stub here is advertising redistributed routes. And if I look at my routing table, the 1 and the 5, I would expect to see those. Both of these are redistributed. One is redistributed static, the other is redistributed connected, but they're still both redistributed. But I should be missing the 4, the 5, and the 6, because those are connected. But I'm getting the 4, 5, and 6. So that's very interesting. There's definitely something. It's like if you configure any option, it's funny because the output, the neighbor detail output shows exactly what we should be seeing. And we're suppressing queries. That makes sense. Let's see what the Wireshark capture shows us here. So coming from router 2, let's see. I need the V4. I think it's this one right here. Let me look at the diagram. It should be 255.2, yeah. Peer stub information, redistributed leak map set. Huh. So that erroneous bit moved down. Because we had summary before and it moved down to redistributed. Now we just have redistributed and moved down to leak map, but we don't have a leak map applied. A leak map is basically like I can say EIGRP stub connected, and then I can leak in other routes by creating a prefix list and matching it to a leak map. And then I can say, even though this is a summary or this is a redistributed route, I'm going to leak that in anyway to override the filter overall. But yeah, it's definitely weird going on. But you know, we'll leave it as it's either a bug with EIGRP, this version of EIGRP. I'm tending to think that's what it is. But the takeaway from this is that you need to understand the effect, right? EIGRP stub by default, when you set up a router as a stub, let me go ahead and do that actually on BR1, EIGRP stub. By default, connected and summary is what is allowed. And they want us to do that actually in V6 as well, which we already did. They also want us to do that on BR2. So let's go ahead and do that on BR2. Router EIGRP 10, EIGRP stub, IPv6 router EIGRP 20, EIGRP stub. All right, so now to verify this, I go back to my HQ, neighbor detail. Exactly what I would expect to see for those peers is what I'm seeing. The peer is advertising connected and summary routes only, and I'm suppressing queries to that particular peer. Even though I know we're going to get more than connected and summary because of that weird issue. All right. You can understand why the stub option that you choose is really very specific to your environment. Suppressing queries is one thing. That's easy. Any stub configuration suppresses queries. Whether you decide to use redistributed, connected. Actually, let me ask you that question because I get a lot of people that ask me that question. when I come in here, what is the difference between saying router EIGRP 10, stub, EIGRP stub redistributed as opposed to static? Okay, static does not mean all static routes. Static literally means static routes that are redistributed into EIGRP. In order for us to advertise routes to appear, they have to be part of the topology table. Static routes by default are not part of the topology table. They have to be redistributed into EIGRP to become part of the topology table. So what is the difference? Why would I choose redistributed versus static? Well, you can redistribute from other things. You can redistribute from BGP. You can redistribute from OSPF. That's where the redistributed command applies. Static only applies to redistributed static routes. So if I did static and redistributed, that would mean not only redistributed static routes, but it would also mean redistributed routes from other routing processes. Make sense? And connected, by the way, doesn't mean all connected interfaces. It means all connected interfaces that are running EIGRP. Because this is telling us what I can send out of the process, right? And like I said, a leak map would, let's say I did EIGRP stub redistributed, but I didn't do connected, which means technically the connected routes shouldn't go out. I can create a leak map that's an exception to the rule, and I can add one of my connected interfaces to that leak map, and I can send out that route and allow the rest of the connected routes to still be filtered. All right, so there's all kinds of interesting things you can do with this. But again, the scenario is very specific to your environment. All right. What's the idea? The idea is that we're trying to, of course, limit the scope of queries, but we're also trying to reduce the amount of routing information that has to be shared between peers. This is born from the idea that most of our branch locations usually are connected with slower speed links and don't have a lot of bandwidth, and we're trying to improve convergence times and reduce the amount of overhead. All right? So go ahead and run your command, show IP EIGRP neighbor detail on HQ. We've seen that a couple of times already, right? That just tells me two things that are important. Connected in summary, suppressing queries. But again, my routing table has my 5 route. Well, the 1 route disappeared. That's interesting. The 1 route disappeared, so redistributed is working, but not static, which is kind of funny, actually. Let's see if that matches the Wireshark capture. It does match the Wireshark capture. Static is a 0, redistributed is a 1. So Wireshark's definitely reading the information correctly. EIGRP is not. What's worse, though, is EIGRP is not parsing their config correctly, because connected and summary are the defaults. Redistributed should not be there. Anyway, you get the idea. All right? So we can see that we're suppressing queries to these peers. This is the v6 neighbor detail output, and only connected and summary routes should be advertised from that peer. All right? Look at the routing table. The routing table should reflect. Actually, in your case, does the routing table reflect anything different? I don't think it does. What they're trying to show you here, this is very important actually. We're looking at the routing table on the branch router. So show IP route, EIGRP. We're not missing any routes. The stub routing feature does not filter incoming routes. It only filters outgoing routes. So I still get to learn everything from HQ. that I'm supposed to learn. Only the incoming routes are filtered. I mean, outgoing routes are filtered. Just said that. Not the incoming routes. All right? So that's the stub feature. They didn't really go into all that detail there about all the different options. But do you guys have any questions about those different options? Static, redistributed static routes into EIGRP, connected routes that are part of EIGRP, summary route that's being advertised out of EIGRP, redistributed routes that include static but also from other routing processes. So you could actually just do redistribute and not do static, and it would still work for the static route. Receive only, nothing goes out. And then leak map allows me to kind of override the behavior by leaking particular routes out. We're not going to look at that configuration. So our next task in this exercise is to go ahead and set up our summaries on our distribution routers. So the first thing they want us to do is look at all the routes that we're getting from the distribution router. Go to HQ, show IP route, EIGRP, and I can even pipe out, by the way, serial 2/0, if I did it right. And these are the three prefixes that I'm getting from the distribution router. We're not doing load balancing because the serial links are artificially changed so they don't equal. Right? So those are the three prefixes that I'm receiving, 96, 98, and 100. Now, let me ask you guys, if I was to summarize this, we could do the same thing for IPv6, by the way, as well. All right, well, that's not going to work because it's multiple lines. I don't think the section will work there. No, because the v6 routing table is formatted a little bit differently, so the line that actually includes serial is not part of the line that includes the route. But if I was to summarize these three prefixes, first of all, which octet am I summarizing to? I could do a /16. That wouldn't be very efficient because that would include a lot of other prefixes, right? So I'm subnetting or supernetting, summarizing to the third octet, right? 96, starting address. 100, that's 5 networks, right? 96, 97, 98, 99, 100. That's 5 networks, agreed? Can I summarize to a block of 5? No. Binary. 1, 2, 4, 8, 16, 32. So can I know the summary is going to be to a block of 8 at least, right? What did I tell you guys about having a block size? What has to be evenly divisible? The block size into the address you start with. So 96, is 96 evenly divisible by 8? It is, which means that's a valid summary. See what I'm saying? I'm going through the iterations of calculating the summary in my head without doing the binary math. I can create a block of 8 starting at 96. I have 5 networks basically that have to be included because I'm going from 96 to 100. That's 96 inclusive, that's 5 networks, which means a block of 8. So what subnet mask would I use for a block of 8? 248 in the third octet. Right, 255, 255, 248.0. You see I'm kind of walking through those steps. You could do the binary math if you wanted to and compare the bits and find where the bits are equal and where they're not equal and create your mask that way, and your summary that way. But that's what we're going to end up doing. We're going to summarize those prefixes, and for the v6, it's going to be these prefixes right here. This one is a little bit more challenging, so I'm going to do this one in Notepad. Actually, I'll do them both in Notepad so you can see everything that I was just talking about. So we're going to be summarizing these prefixes here. And we're going to be summarizing the serial prefixes here. And we've already agreed that the summary here should be 192.168.96.0 with a mask of 255.255.248.0. That is a block of 8 starting at 96. Make sense? How do I know it's a block of 8? Because 256 minus 248 is 8. Every octet is 256. 0 to 255. But what about these guys down here? Do we agree that the summary is going to start with 2001? DB8? 0? Isn't that common to each one of these prefixes? 90, 91, 92. Now this is a little bit more challenging because these are not decimal numbers. These are hexadecimal numbers. So this one, it might be a little bit easier to do it in binary. 90 is actually technically 0090. 91 is 0091. And 92 is 0092. And in binary, 90 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 91 is the same thing. Oops. With the last bit changed. And 92 is the same thing with the second to last bit changed. Make sense? Remember, these are hexadecimal values, which means they're 4 bits each. So this becomes my summary boundary. Make sense? Which means 0090 double colon slash 62. You understand how I got that? How I'm getting the masks, okay. This mask I kind of calculated in my head, but I can break it down from a binary perspective. 192.168.96.0, 192.168.98.0, 192.168.100.0. Okay? So we agree that the summary is going to start with 192.168. If I take 96 and I convert it to binary, that's 011000000. That's 96. 98, 011000010, and 100, 011000100. Make sense? Well, it's 96 is 64 and 32. That's actually a pretty simple one to calculate, but I just know what the columns are. So this is 96, which means my summary boundary is here. Agreed? And the value of those bits to the left is 96. We got the 248 because the summary, the mask, is basically how many bits match. 8 plus 8 is 16. 17, 18, 19, 20, 21. So actually it would be a slash 21, which is equal to 255.255.248.0. Slash 20 is 240, slash 21 is 248. Same thing for the V6. Well, yeah, you got to remember that the double zeros are still there. So for the V6 addresses, this is 4 zeros. There's 2 zeros in front of 90. They just took out the leading zeros in the hextet. So what I did is I wrote down the full hextet, and then I wrote down the binary equivalent of each of those hextets, and I came up with my boundary. 16 bits plus another 16 bits is 32, plus another 16 bits is 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62. So basically these two bits on the right can be anything. The bits on the left are fixed because they're part of the summary. Make sense? So that's how we calculated our summaries, and then they do break it down in the book here. They do their binary conversion, and then the subnet mask doesn't really matter on the original route because we're not comparing masks. We're comparing bits in the address, in the network, in the prefix. So we don't care what the prefix length is. All right? 21 bits are common for all the networks. The nice thing about writing it out like this, though, is that you know what's included because the last 3 bits in this octet can be anything, which is 96 all the way up to 105. Because this is 100 plus 2 plus 1, 103, excuse me, not 105. 103, which actually makes sense because 96 plus 8 is 104. So 103 would be the high end. So once we've actually calculated the summaries, the next step then would be to actually implement the summary. And we use what we call the summary address command to do that. All right? We're going to do this on our distribution router. So let's go ahead and go into our distribution router. We're going to go into our router EIGRP Cisco. Oh, dang it. Just started another process. Cisco, address family, IPv4, autonomous system number 10. Now notice where the summary is applied. The summary is applied at the interface level. In EIGRP, summaries are applied at the interface level. In OSPF, they're applied to the area on the ABR, right? We use the area range command, and that's how we do our summaries on an ABR. We're using serial 20 and 21, by the way, not 00 and 01. And we say summary address, and we put in our calculated summary. And you could enter the mask in dotted decimal format, or you could put the mask in prefix notation. Now, I've only applied this to one interface. Watch what happens on HQ if I don't apply it to the other interface. It's a very bad thing, actually. Serial 20 is our preferred interface, isn't it? That's the interface in our topology that has more bandwidth. If you look at the topology, serial 20 has 2 megs of bandwidth. Serial 21 is artificially set to 1.5 megs of bandwidth. So we should be using serial 20, but look what happened on the HQ router. Show IP route EIGRP. The 9621 is coming in on serial 20. The remaining prefixes, which are not summarized, are coming in on 21. When I send a packet to the 96 subnet, guess where it's going to go? Is it going to go over the /21 or is it going to go over the /23? It's always going to choose the more specific. Even though that's a worse metric, we don't care about the metric at this point. If the route is a longer match, we use that route. The reason why this is important, obviously you understand why this is important, is if I don't apply the summary appropriately, it could end up resulting in suboptimal routing, which is what's happening in this case. 96.1 will use the serial 21 interface instead of using the summary. So that's why we're applying it to both AF interfaces. Now, once I apply the summary to both AF interfaces, if I go to HQ, only one of those routes is going to show up. And that's again based on metric choice, not based on longest match choice. The metric for 2.1 is larger than 2.0, so the 2.0 route gets put into place. Make sense? All kinds of things you have to kind of consider when you're dealing with this optimization stuff. So now we have a summary. Guess what's configured on the distribution router? We saw this. Did they have us do it for v6 as well? I don't know. Let me see. They did not. Okay. They probably will eventually, but yeah, they do. That's the next step. All right. So guess what got created on the distribution router as well? We talked about this in the Encore section. Do show IP route on the distribution router. Pipe include null. A null zero route got created. You guys remember what the null zero route was for? It's a bit bucket. It's a loop avoidance route, so that if the summary includes networks that I don't actually own, when packets come to me for those particular networks, they'll match the null zero route because it's the only route left to match, instead of matching like a default route and then getting looped back, and those packets will get dropped. That makes sense? All right. Yeah, so far so good. So far so good. I'm just trying to think if there was, now actually, we didn't do, yeah, it's okay. We didn't do stub configuration on the distribution router. I was thinking that we did stub on the distribution router, but we wouldn't anyway because it has multiple connections, multiple paths. All right. So now let's go ahead and take a look at the v6 configuration. Show IP route on the distribution router. What they're trying to demonstrate here is the null zero route, which I just discussed, right? Remember that null zero route is a bit bucket. It's a loop avoidance mechanism. So if my summary includes addresses or prefixes that are not routes that I'm originating, then we're going to match the null zero interface. What about the metric for the summary? If I go to HQ, we did talk about this as well. There is a metric for this route, 6395301. How was that metric calculated? It's based on the best metric of all the routes included in the summary. Now, in our particular case, it's the same network, so it's going to be the same regardless. The three networks, if I do a show IP EIGRP topology, and I include 96, pipe include 96.0 and 98.0 and 100.0, you can see that they all have basically the same metric, 163840. All right, so that summary, the metric for the summary, the seed metric for the summary is this number. If this /23 here had a slightly lower metric, then that would end up being the seed metric for the summary, even though there's other routes included that have a higher metric. The best metric of all the routes included in the summary is the seed metric for the summary route. How come this number doesn't actually match the HQ number? This says 6395301, and these say 163840. You guys know the answer to this. How come it doesn't match? This is the local metric. This is the metric of that local seed metric plus the cost of the serial link. We have a link in between the routers that has to be considered as well. See what I'm saying? All right. IPv6, we did the summary calculation for IPv6. This is just a tabulation breakdown of that. The first 62 bits match. And as far as the actual command to implement the summary, it's identical. We're going to go into the EIGRP process on our distribution router. Okay. We are going to go into our IPv6 address family. And we're going to do our summary address command for AF interface serial 20. And we're going to do our summary command here. Same calculation, 62 bits match, summary address. And we'll do the same thing for 2.1. Just as I mentioned before, if I didn't do it on 2.1, I would see those individual prefixes coming in on 2.1. I would end up using those prefixes instead. Just like before, if I do a show IPv6 route pipe, include null 0, I can see a null 0 route was created. Let's just do a show IPv6 route, because again, the routing table here is a little bit different. Where's that null 0 route? Loopback, 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 serial, 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 direct, direct, direct. Where the heck is it? Loopback, loopback, serial, serial, serial. This is the null 0 for multicast. That's not the one we're looking for. It's been a long day, so my eyes are not working. I passed over it like 3 times. There it is right there. All right. Also notice what the default local administrative distance is for a null 0 route. 5. It doesn't stay 5, it becomes 90 on the other routers, but that's interesting. It's kind of inserted into the local routing table with an AD of 5. All right. And if I go to my HQ, I will see the summary. I'm not going to run these commands because I think you guys pretty much get the idea here. The 96 is coming in as a /21. And that metric doesn't look the same. Let's see. No, it's not the same metric. Interesting. I mean, it's not a big deal. The concept of the lab is still functional, but I'm just curious why that metric's not the same. Same thing for the V6. We're going to see the /62 right here, and that's coming in with that same metric, 127.406.40. I'm not sure why it's coming in that way, but all right. Any questions about the summaries? The benefit of doing the summary is, number one, it reduces the size of the routing table. It does not reduce the size of our local topology database or our local routing table, but my neighbors, it will reduce the size of their information. And it also helps to further eliminate the need for queries. Because if the summary doesn't change, and that's the only route I know, then even if an individual prefix within the summary fails, I don't have to send a query because I didn't get a new route. I still have the same route. So the last task in this exercise, the last task for today, is, because I know it's already a little bit late, is to talk about the default routes. So let's go to HQ. Let's see what kind of static route we have on HQ. Show IP route static. And you can see that we actually have a default static route that points to 209.165.201.1. That's just the simulated internet connection that we're trying to get to. Okay. So we do have a static default route. And we will have a similar one for V6. Show IPv6 route static. We see our static default route. Notice that's just a :/0. What does the :/ represent in IPv6? All zeros. 128 bit of zeros. Or it doesn't mean 128, it just means that whatever's left over is zeros. In this case, it's 128 zeros, and the /0 is the mask. So that's basically a default route. So there's a couple ways that we can inject the default route into EIGRP. I think the best way is to simply statically assign the default route to the local router and then do a redistribute static. The problem with doing a redistribute static is it might end up including other routes that you don't want to include. So if I was to do it this way, let me see how they do it in the book here. Yeah, they just do a basic redistribute static. And that's it.
Is that all static routes?
Yes, when you do redistribute static, it's all static routes. All right? So let me show you how I would do this if I only wanted to inject the default route. All right? And not all static routes. So we already have the static routes on HQ, but what if I had some other static routes I didn't want to redistribute? What I would have to do is I would have to create an IP access list standard. And I would say, I'll just do this for v4. v6 is slightly different, but it's the same concept. IP access list standard default permit 0.0.0.0. And I don't want to do a 255, 255, 255, 255 because that would be all routes. I want to do a mask of 0, 0, 0, 0. So this is matching the default route specifically. All the bits have to be 0. Okay? And I would do a route map default permit 10 match IP address default. So I'm creating a route map that permits whatever I'm applying the route map to, and I'm referencing that default access list. And then I'm going to go into router ROUTER, router EIGRP 10. Oops, sorry, we're using Cisco. I'm going to go into the address family for IPv4, autonomous system number 10. And the question is, am I doing the redistribution under the address family or am I doing it under topology? Well, I'm inserting routes into the topology table, which means that I would do it under topology. Redistribute static route map default. So I'm saying go ahead and redistribute static routes, but only the ones that are permitted by the default route map. And the default route map is referencing the access list, which is only the default route. We're going to go into this later on, day number 3. But that's kind of a better way of doing it as opposed to just doing redistribute static, unless you want all the static routes to go in. You guys can just do the redistribute static if you want. But if I go to my distribution router now, show IP route, you can see I'm now getting a default route through EIGRP. And it's coming in as a DEX route, which means I know that it was redistributed. See what I'm saying? So let me just show you the whole config. Show, run, pipe, include, or section, route map, pipe access list, pipe router. So I should have done the access list first, but so did it even give it to me? Yeah, it did. It put it at the bottom. So here's the access list matching the default route. It took out the other quad 0 because with a standard access list, it assumes a host if you put a quad 0 mask, so it just took that out. Here's the route map that's matching the access list. And then here is the redistribution of the static routes based on what's permitted by route map default. So there could be other static routes I want to allow in. I just have to add those routes to the access list now, and those would be allowed in as well. All right. So they created the default routes. All they did is they just did a redistribute static. We know what the effect of that is. The key here is, why is it under topology base? Because it's affecting my EIGRP rib. It's affecting my EIGRP topology table. I'm putting routes into my EIGRP topology table. So that is something that I would do under the topology based configuration. All right. Also notice here, usually when redistributing into EIGRP, the initial seed metric must be specified for redistribution to work. That's if you're coming from another routing protocol. But we are doing it based on a static route. And the static route points to an interface, which means we can derive the seed metric from that interface. Connected and static routes do not need a seed metric. Other routes, and we're going to get into this when we go into our redistribution section, other routing, if I was to say redistribute OSPF or redistribute BGP, I would have to specify a seed metric, otherwise it would be infinite. In this case, EIGRP takes the metric values from the outgoing interface that's technically associated to the route. Static route points to a next hop points to a connected interface. All right. And then the last step, they just want us to verify that the route's actually propagated, which we already did. We can see the route there in BR1. I didn't do the V6 one, but it's the same concept in IPv6. It's going to show up as an EX route, which is external, has an AD of 170, and then this is the actual route. All right. The asterisk always simply indicates that it is a default candidate, default route. And then the last step, I'm not running these commands because we're getting a little bit long here on the time, but a ping should work because this is the external network. So if I go to my distribution router, I should be able to ping. No problem. And I can ping. All right. So that concludes that discovery. Next time we get into class, we're going to get into what load balancing is. Tomorrow we're going to do variance and ECMP as well as UCMP. So we'll see you guys there. All right, in this subsection, we're going to talk about adding an additional level of efficiency by allowing for load balancing and authentication with EIGRP. EIGRP actually has the capability to distribute traffic over several different links. And that's not really uncommon to an IGP routing protocol. Most routing protocols outside of BGP, of course, have the capability of supporting load balancing over equal cost multiple paths, right? Where we have separate paths that have the exact same metric. But EIGRP actually has the capability of doing what we call unequal cost metric load balancing, or UCMP, unequal cost multipath routing. Load balancing is a way for the routing protocol to distribute traffic across multiple links at the same time. Now keep in mind, when we talk about load balancing with EIGRP or load balancing with OSPF, those are concepts that are native to those particular protocols, but you also have to consider data plane load balancing techniques as well, specifically load balancing with Cisco Express forwarding. That's a very important concept to understand. The load balancing techniques that EIGRP might use or OSPF might use might be trumped by the load balancing technique that some sort of distributed hardware-based forwarding might use or Cisco Express forwarding might use. So in this particular section, in this case, we're talking specifically about layer 3 control plane traffic load balancing as opposed to data plane load balancing. Now, EIGRP by default supports up to 4 equal cost paths in IPv4. That can be extended to up to 16 paths, and in IPv6, 16 paths by default, up to 32 or 64 paths, depending on the type of iOS that you're using. And you can use two things to configure this, and we'll take a look at this in our discovery as we go through the discovery a little bit later on, right? We can use maximum dash paths. This would be something done under the topology base for named mode configuration, or under the global routing process for classic mode configuration. But maximum paths allows us to identify how many paths we're going to be able to use for our load balancing scenario. If we set, for example, a maximum path value to 1, that effectively disables load balancing in that particular case, or I could extend it up to, depending on the iOS version and the platform, obviously multiple paths. When the packet is process switched, meaning that the packet is switched at the CPU level, load balancing over equal paths occurs on a per packet basis. If we're doing fast switching, meaning that we're switching at the data plane, load balancing over equal metric paths occurs on a per destination basis. And that is more of a characteristic of Cisco Express Forwarding, although Cisco Express Forwarding, depending on the platform, supports different options for load balancing. We can do per packet or per destination, and Ceph is enabled by default. There's a great document if you go out to Google and you search on Cisco Express Forwarding breaks load balancing. That's not the actual name of the document, but it always seems to pull up that very first document that Cisco published, which is a best practice consideration document in dealing with load balancing with Cisco Express Forwarding in conjunction with some sort of process switched packet load balancing that we would do at the network layer. All right, so the first diagram, pretty straightforward. R1 is able to load balance because these are equal cost paths. And this is not unique to EIGRP. RIP can do this, OSPF can do this, ISIS can do this. So it's not unique to the EIGRP. If I want to load balance over unequal metric links, which is disabled by default, I'm going to use another topology-based configuration command, or global routing process configuration command called variance. Variance is a command that tells the router to include routes with a metric in a specific range, right? So we take our successor. Let's say that I've specified a variance of 3, okay? And that's a multiplier of 3. That's an integer that we're multiplying against the feasible distance of my successor route. So let's say that the feasible distance of my successor route is 10. That means that with a variance of 3, any metric between 10 and 30 would be considered usable, and all of those routes would become successors. And then we would do load sharing across those links based on the relative speed and bandwidth in the group. Keep in mind though, variance gets applied only after the feasibility condition is checked. So if a particular path falls within the scope of the variance, but that path does not meet the feasibility condition, it cannot be included in the load balancing scenario. The path has to meet the feasibility condition first. All right, only feasible successors or feasible successor candidates can be included in the load balancing scenario, because again, we want to make sure that we have a loop-free topology. All right, so we're going to do a discovery that takes a look at those concepts as well. And then let's take a look at EIGRP authentication. So this is another concept. I don't know that this would really classify as a scaling technique necessarily for EIGRP. It doesn't assist us in actually scaling the protocol, but it certainly protects the protocol from a route injection attack or denial of service attack from other devices in the topology that are trying to spoof or simulate EIGRP peers. When I enable authentication, every single datagram, every packet that gets exchanged between the neighbors is going to be authenticated. And this is basically the way that it works. Let me go ahead and pull up my paint tool here. So let's say we have a router here, and we want that router to communicate. Let's get a better marker here. Let's do a pencil. and 2D brushes. Let's do undo. There we go. So let's say we have a router here, and I want that router to exchange information with this router. Okay, so I've got essentially a router on the left that wants to exchange information with the router on the right, and that could be a hello packet. It could be an update, a query, a reply, whatever it might be. Now, normally those packets would be sent in plain text, in the clear to the neighboring router. When I enable authentication, I'm adding this hashing process. In our case, it's MD5. We have the same MD5 process happening on this side, and then on both sides we have some sort of secret keying material that is pre-configured on each of the routers. Graphics are kind of zoomed in here, so it's a little bit pixelated there, but you get the idea. All right, so we've got this MD5 process that's created. Now, I want to send my hello packet. What I do then is I take that hello packet, I'll just put an H for hello, and I stick it into the hashing process along with the key, and I come out with a message authentication code, what we call an HMAC. Right? Basically a hash of the information that was sent or that is being sent. And I send that HMAC along with the hello message in the clear. The router on the right receives that hello packet. It has a key that it has configured, so it runs the hello through the hashing process with the key that it has configured, and it comes up with an HMAC value on the other side. And what it does is it says, okay, if this HMAC, let me do a different color here, is equal to the one that I received, then the data has been authenticated. Not only has it been authenticated for the source, because the only way the source could generate the hash is if it had the same key, but it also authenticated the integrity or verified the integrity of the data, meaning that the data wasn't modified in transit as it moved from one router to the other. So keep in mind when we're talking about traditional routing protocol authentication, we're really just talking about the ability to verify the identity of the source as well as to identify the integrity of the information. All right? Which means that we have to have identical pre-shared authentication keys, the neighbors have to be using the same authentication method, and so on. Now, in EIGRP, traditionally we do support MD5, Message Digest 5. That's going to generate a 128-bit message digest based on a static input with the keying material in the message. But in named mode, we can also use MD5, but we can use SHA-256, which is a 256-bit digest, which is going to be a little bit more secure. Now, as long as you're using strong keying material, the hashing process is relatively secure. The only way you can break the hashing process is through some sort of rainbow table attack or brute force type of attack where you're trying various combinations of key strings and data to see if you can generate a common hash. Maybe with a collision you could do the same thing, find some sort of keying material that might match if there happens to be a collision with a hashing process. All right? So again, it's not really an efficiency thing that we're getting here. It's more of a functional thing. We're trying to ensure that we don't have other routers trying to kind of impose themselves into our routing domain. So what you're seeing in this particular graphic here is one of the options that we have for configuring authentication. And we'll take a look at a couple of the different options as we go through our discovery. That's part of our process in our discovery. In this particular case, we're using a global keychain. Now the keychain name is locally significant to the router. It does not have to match on both sides, so this is a locally significant keychain. Keychains are actually used in other protocols as well and other processes, so it's not specific to EIGRP. You would actually create the keychain the same way whether you're running named mode or classic mode EIGRP authentication. We've got a keychain, and then we have a combination of what we call a key ID and the key string. This is a very important concept because the key ID and the key string need to match on all of your peers, or at least the peer that you're authenticating with. We don't send the key string in our messages. The key strings are kept secret, locally configured on the router and not shared. But we do share the key ID. So in order for me to authenticate a message from a particular peer, I need to make sure that the particular key ID matches the key string that I have configured based on the key ID that you specified in the packet. And that key ID number is actually going to be carried inside of the EIGRP packet header. We'll see that in a Wireshark capture when we get into our discovery here in a couple of minutes. Notice here that they've applied authentication. We're running classic mode MD5 authentication in this particular case. I've specified the mode, even though with classic mode you don't really have an option to specify anything else. We're applying the authentication to the autonomous system number, and then I'm applying the keychain to the authentication process. Without applying the keychain, there is no default key, there's no default authentication. The neighbor relationship would not form until we've identified an appropriate keychain. One of the things we'll take a look at in the discovery is the ability to specify not only a send lifetime, but an accept lifetime for specific keys as well. So the reason why we would have a keychain is it provides us the ability to create multiple keys within the chain, and certain keys will be active based on certain times of the month or certain times of the day, usually weeks or months or what we specify. We don't want to rotate through keys too quickly. Obviously, in that particular case, one of the most important concepts is network time, right? You want to make sure that the network telemetry information is accurate on your platforms, because if your keys are time-based, you're going to need to make sure that the clock is configured appropriately. Notice that under the global routing process, we don't really specify anything unique when we're doing authentication. Authentication in EIGRP, unlike OSPF, which can be done throughout the area, in EIGRP authentication is done on a per neighbor basis. All right, so it's actually a relatively simple configuration. We specify the key chain. Each key is identified with a number, which is the key ID. And that is an important concept, that those things have to match when you're configuring both the key chain and the key ID. We'll also look at how we can verify that information and make sure that information is accurate a little bit later on. The authentication mode, like I said, in the case of classic mode, we only have MD5 as an option, and we're using autonomous system number 110 in this case, and then the authentication keychain gets applied. We can also do a similar thing with IPv6. We'll take a look at that configuration on the next page here. This is our authentication with IPv6. It looks pretty much the same. In fact, it's basically identical. The only difference is we're using a keyword of IPv6 instead of IPv4, which allows us to specify the authentication based on the IPv6 peer, not the v4 peer in this particular case. Again, this is classic mode configuration. All right, so if I was looking at this kind of side by side, we have a configuration here on the next page actually that kind of shows the side by side configuration. In this case, we're looking at named mode, so it's slightly different. We still create the keychain globally. That again is not going to change in named mode because the keychain is not specific to EIGRP. It is something that can be referenced from several different processes. But under our named mode configuration, we can apply the keychain, and this is the point where we can actually apply that SHA-256 authentication or hashing process as opposed to MD5. So it does provide us kind of a little bit more capability. We would use the authentication mode HMAC SHA-256 command, not the authentication mode MD5 command. Notice we can also apply a password directly to the end of the statement. I don't have to use a keychain. I could say authentication mode MD5, and then I could specify the key string as part of the authentication mode command. And we could do the same thing with our SHA-256. We certainly recommend using key strings because key strings give you a lot more flexibility with regard to how you control which keys are used, so you're not always using the same static key, but it is an option. You don't have to set up a keychain to be able to establish authentication. So what we're going to do is we're going to go into our final discovery of this section, section number 2. We're going to take a look at configuring EIGRP load balancing and authentication in Discovery 4. And we're going to do a kind of a deeper dive into looking at, again, the specific configurations. I'm going to show you a lot of different configuration options and stuff we didn't talk about in detail in the introduction section. So I'll see you in the Discovery. All right, welcome everybody. We're going to go into Discovery number 4. In this Discovery, we're going to focus on doing EIGRP load balancing and authentication. It's a pretty straightforward Discovery. We're not going to be doing too much outside of the scope of this Discovery, but I will show you some additional things that I think are important to understand as part of our discussion here. But basically, our goal here is to set up some load balancing. We're going to take a look at this in named mode for both v4 and v6. We're going to set up EIGRP authentication in classic mode and in named mode, so you can kind of see the difference there. We have 4 routers in the topology, HQ, BR1, BR2, and our distribution router. All the devices have their basic configurations in place, including the host names, addresses, and so on. All right, so our first task in this exercise is to enable IPv4 and IPv6 EIGRP load balancing on our HQ router. We have these 2 links here, but notice that the 2 links are not equal, right? One is 2 megabits per second, one is 1.5 megabits per second. So that means we're going to have to set up UCMP, or unequal cost multipath, so that we can achieve our load balancing. We're going to enable MD5 authentication between BR1 and HQ. We are going to use keychains and set up time-based authentication between BR2 and HQ, where we're going to set up a keychain and establish both our send and accept lifetimes for the keys. We're also going to enable SHA-256 authentication for EIGRP on our distribution router and our HQ router. Hopefully this iOS supports that. If not, we'll have to just take a look at it in the context of the Discovery. All right, same basic topology that we've been using for the last couple of Discoveries. A couple of WAN links between the distribution router and the HQ router. A couple of Ethernet WAN links between branch 1 and branch 2 and the HQ router. All right. So we're going to start by taking a look at reachability. And this is something that I always suggest that you confirm before you do anything else. Before you go in and you start to make modifications and you start modifying the configuration, whether it's adding load balancing or whether it's adding authentication, I always suggest that you first verify basic functionality. Because as you add layers of configurations, if something ends up not working and you didn't test it beforehand, you have multiple things that you're going to have to test, as opposed to just assuming that, oh, well, I just didn't do my authentication correctly because everything worked before I applied authentication, and now nothing is working after I've applied authentication. Does that make sense? So we're going to do a ping. We're going to ping essentially those networks that exist from on the distribution router from HQ. So let's go into our HQ router here. And we're just pinging this essentially loopback 0 on the on the distribution router. So 96.1 is reachable, and the 90:1 will be reachable as well. That just kind of tells me that I do have reachability across that link. Now, are we using both links in this particular case? If I do a show IP route, 172.16, 96.0, I can see that I'm not load balancing in this particular case. I'm actually only using one route option to reach that destination, and that is from 255.10, which is the 2 megabit per second serial link, serial 20. Okay? The minimum bandwidth across the path is 2,048 kilobits. The delay is 20,001 microseconds, which is 20,000 for the serial and 1 microsecond for the loopback. So we're not doing load balancing at this point, but that would make sense because they're not equal cost paths. I would also be able to see that if I just went ahead and looked at the routing table. And I looked specifically for the 96 subnet, and we can see that we're only using serial 20 in this case to reach that 96.0 subnet. Same thing for IPv6 route EIGRP. The 90 subnet we see right here, and again, only the serial interface is being used to reach that particular destination. Okay? So there are two links between the HQ and the distribution router, but because they're not equal as far as bandwidth goes, they don't both get inserted into the routing table. We also want to make sure that before we decide that we're going to implement unequal cost multipath routing, that we actually have another path that could qualify within the scope of the unequal cost algorithm that we're going to establish. So I'm going to do a show IP EIGRP topology. And what I'm looking for in this particular case, specifically for the 96 subnet, which is here at the top, is do I have a feasible successor? If I don't have a feasible successor, it doesn't matter. Doesn't matter because the only paths that are allowed to be utilized for unequal cost multipath routing are the paths that qualify as feasible successors. Or they meet the feasibility condition, I should say, right? Maybe they're not the feasible successor, maybe they're the third in line or the fourth in line as far as the destination goes, but as long as they meet the feasibility condition, they can be used in an unequal cost multipath routing scenario. So the top path, let me see if we're matching up here. Hey, we do match this time. 16308, 17352. So the top path is definitely the preferred path. It has the lowest feasible distance. And the bottom path qualifies as a feasible successor because the reported distance of this path, which is 163.840, is less than the feasible distance of the successor. So let's say that I did want to use both of these paths. What type of variance would I have to apply at a minimum in order for that to happen? Well, remember, variance is a multiplier against the feasible distance of my successor. So if I said, for example, I take this number here, 163.080.1920, and I multiply that number times 2, that should do it, right? So 3261.603.840, that's definitely more than 173525787.8, right? You guys agree? Unfortunately, with EIGRP and the UCMP concept, we can't really get any more granular than full integers. So we can't multiply by 0.5 or multiply by 0.3. It has to be an integer of 1, 2, 3, 4, all the way up to 128. So we've already checked all the boxes. We know that we have an alternate path that meets the feasibility condition. We verified what the variance would have to be in order for these paths to both be considered equal, or at least to both go into the routing table. So the only remaining task then would be to go ahead and configure this UCMP configuration. We can look at our v6 topology as well, but it's going to be exactly the same. Show IPv6 EIGRP topology. It's not going to be any different for the 90 subnet. Same metrics, because the metrics calculated the same way. And again, this second path meets the feasibility condition. All right, you can actually configure, because we are running dual stack, you can configure load balancing for one stack without having load balancing enabled for the other stack. You don't have to have load balancing enabled for both stacks. It makes sense to do that, but you don't necessarily have to do that. All right? So we see the same conditions here as well. All right, EIGRP topology tables reveal that HQ received information about the destination networks 96 and 90 over both serial interfaces. Because the route over the serial interface of 2.0, in our case, has the lowest feasible distance of 163.0.81920, it is selected as the only successor. Because the default variance in EIGRP is what? 1. Which means only ECMP is supported. Only equal cost multipath routing is supported because the default variance is 1. The other route that was received over serial 2.1 in our case has a higher feasible distance, 173.525.7878, because it has lower bandwidth. It's artificially set, right? If I go to HQ and I do a show run interface serial 2.0, we can see that the bandwidth has been elevated for this interface. Normally it's 1.544 megabits per second. Show run interface serial 2.1, the bandwidth is not applied, so this has a default bandwidth of 1.544. So we've artificially inflated the bandwidth of this serial interface to make it appear as though it has more speed, which means it has a lower metric overall. All right? By default, only equal cost load balancing is enabled. For unequal cost load balancing, we have to change the configuration. All right, and as we mentioned before, if we're dealing with named mode EIGRP, we have a 64-bit wide metric. All right, and that metric if we look at the route in the topology table, is a true representation of how that metric is calculated based on the 64-bit scale that we have for EIGRP for named mode. But we're dividing that value by 128 by default so that when we insert the route into the global rib, the number will fit in the 32-bit field that the global rib presents. All right, that's the scaling factor that we talked about yesterday that allowed us to scale down the actual metric for the route. So if I did a show IP route and I look for the 96 subnet here, which is right here, you can see that that metric is significantly lower than what was represented in the topology table. Again, it's just this is a number that was derived from dividing the feasible distance in the topology table by the rib scaling factor, which is 128 by default. It doesn't change, by the way, our overall objective, right? Because when we apply variance, whatever that variance value is, we apply that variance based on what's in the topology table, not what's in the global rib. The variance allows us to define what gets established and goes into the global rib. So we always will look at the values that are listed in the topology table to determine how we're going to do the load balancing and how we're going to extract routes from the topology table and put them into the global rib. Does that make sense? All right. So, I mean, they mention this here in the book, but it's not really that relevant, quite honestly. It's not something we consider or concern ourselves with too much. EIGRP can balance across multiple paths that have different metrics. The successor is always used as the kind of the starting point, right? What is the feasible distance of the successor? What is that value? Because the variance is going to be applied against that particular value. All right, now the defaults here for variance is 1, which means 1 times whatever that number is, which means equal cost multipath routing, but we can always go all the way up to 128. I've never seen a scenario where you'd want to go up to 128, right? That's a pretty significant multiplier when you're talking about dealing with numbers as large as we are, right? We're not multiplying 128 times 10. We're multiplying 128 times 17584587887, whatever, right? So it's a pretty significant gap, all right? So EIGRP is always going to put the successor route into the global rib and then additional feasible successor candidates, meaning that other paths that meet the feasibility condition if they fall within the variance threshold, then they can also be inserted into the global rib. All right? But if a path does not meet the feasibility condition, even though it falls within the variance scope, it will not go into the global rib because EIGRP is not assured that that path is a loop-free alternate path. All right? And it doesn't go through a secondary check. It doesn't say, well, okay, you fall within the variance, so let's go ahead and verify that you're a loop-free alternate path. No, EIGRP doesn't do that. If the path does not meet the loop-free alternate criteria, that feasibility condition, then it doesn't matter if it falls within the variance. It's not going to be applied. Okay? So the route has to be loop-free. That condition has to be satisfied before we can even apply the variance to that particular path and consider putting it into the global rib. All right? Default variance is 1, which indicates that we're going to be doing equal cost multipath routing. If the variance of 2 is applied, then it's basically a multiplier against the feasible distance of my successor. Keep saying this over and over again, but you get the idea. If the feasible successor or the feasible distance of the successor route is 20, a variance of 2 means anything from 20 to 40 would be considered equal at that point. All right? Says here also that the EIGRP routing protocol itself is not responsible for load sharing traffic between multiple routes. EIGRP is a control plane process that installs routes in the routing table. Yes and no. Okay? Yes by default, no if you turn off Cisco Express forwarding. What they're referencing here is they're saying that once the paths get installed into the global rib, Cisco Express forwarding will take that information and will build the adjacency table and the FIB, the forwarding information base, based on what they see in the global rib. And then Cisco Express forwarding is going to be responsible for performing the load balancing across those links based on whatever load balancing algorithm that you decide that you're going to use. All right? In the Encore class, we talked a little bit about Cisco Express forwarding and switching and how it keeps everything at the data plane instead of sending it up to the CPU for process switching. If I turned off Ceph, all my packets then have to be processed at the CPU level, which means EIGRP in that case would be responsible for doing load balancing. Because everything is process switched, it's not fast switched at the data plane. All right, but by default, we are, Cisco Express forwarding is doing the actual load balancing, which may or may not be a good thing. I'll talk about what that means for us in a little bit here once we go through and do our configuration. All right. Now we are running on HQ, we are running address family configuration or named configuration. So we need to apply the variance to the address families independently. Remember what I told you guys yesterday about this? When we're modifying anything that has to do with building the topology database or interpreting the information in the topology database, we apply that to our topology base configuration. So we're going to go ahead and go into our HQ router, go into router EIGRP Cisco, and address family IPv4, autonomous system number 10, topology base. And we're going to say variance. And again, we can specify a variance value from 1 to 128. We're going to go ahead and do a multiplier of 2. And I'm going to go into my address family IPv6 autonomous system 20. And I'm going to go into my topology base and apply the same configuration. Okay, that's it. I'm done creating the load balancing scenario for EIGRP on this router. But we're not done by any means because there's a couple of considerations to take into account. All right, I'll give you guys a second to get that configuration applied. While you're doing that, I'll go ahead and go through the description here. So in order for us to consider that this path here, which is the 1 over serial 20, is equal to this path, the 1735257878 needs to fall within the variance that we apply. Well, because we're dealing with such large numbers, 16308011920, a multiplier of 2 does that. And we did that calculation as part of our initial discussion, right? Multiply 16308011920 times 2, and you get a fairly large number that's inclusive of the 1735257878. All right? So that's pretty much it for applying the variance on this side. Now if I go and look at my topology table on the HQ router, show IP EIGRP topology, and specifically looking at 96, you'll see that we now have 2 successors. Even though the feasible distance of these paths are different, they now both qualify as successors because of the variance applied, which means if I also look at my routing table, show IP route 172.16.96.0, you can see that both routes have been inserted as in my routing descriptor block as possible destinations. Now you'll also notice here that EIGRP is pretty smart about this, right? We see that we can go through the 14 network, which is serial 21, that's the slower speed link, right? That one has a bandwidth of 1544. Or we can go through 255.10, which is serial 20, which has a bandwidth of 2048. So these links are not equal. They're not considered equal. The metrics, these are the scaled down metrics, but the metrics are not the same. But because we've applied variance, then we know that we can use these. But notice that EIGRP is smart enough to say, hey, these routes are not the same. Traffic share count for the faster link is 120. The traffic share count for the slower link is 113. Now that doesn't mean for, say, every 120 packets on one link, I'm going to send 113 packets on the other link. It's not what that means, but it is a ratio. And it does define that we're going to utilize the faster link more than we're going to utilize the slower link. Does not mean the same here. Well, I guess technically it does, right? The question was, does the asterisk in this case mean that that's the best path? Yes, it does in this case, but we are still utilizing both paths, right? And the asterisk also indicates that this is the normal successor, which is the same concept, right? So now EIGRP has the ability to recognize that there's a difference between these two links. Again, because we have Ceph operating, right? If I do show IP Ceph, I can see that for the 96 subnet, let's find it here. Where is it? Should be in here somewhere. Right here. So for the 96 subnet, Ceph recognizes that both interfaces are usable to reach that particular destination. All right? This is what they were referencing in the book. This means that Ceph is going to be responsible for doing the load balance, not EIGRP. Which is kind of an interesting thing, because if I did this, let me show you how Ceph kind of breaks this per packet load balancing concept that EIGRP has. If I do a show interface serial 20, and specifically I want to look at the packets per second, okay? So let me copy output rate here, and I'm going to do a show interface serial 20 pipe include this output rate, and I'll do the same thing for 2.1. And I'm going to start to generate some traffic. So I'm going to generate traffic from my loopback on HQ. Well, I can just use, do I have a loopback on HQ? Show IP interface brief. I do not. So I'm just going to generate the traffic from my Ethernet interface. So I'm going to do a ping to a network behind the distribution router. So we'll do 96.1, 172.16.96.1. And I'm going to do a repeat of 1,000 and a size of 1,500. And I'm just going to generate a bunch of traffic, right? Now, if EIGRP was responsible for doing this load sharing, then EIGRP would basically be utilizing both links. All right, but now if I go and look at the output rate, you can see that every single one of those pings went over serial 2.1. Because Ceph does per destination or per flow load balancing. So it looks at, and depending on what Ceph load balancing, show load Ceph load balance. Let me see, what the heck is the dang command? Show IP Ceph. Let's see, I thought it was just load balance. Sorry? No, it's not load info. I can't remember the dang command. So maybe show IP Ceph internal. I know there's another command. I can't think of what the heck it is. But in any event, the algorithm that Ceph uses is based on flow information. It's not based on per packet. So if every packet matches the same or has the same characteristics, Ceph is going to end up utilizing that same link for that flow. That's something in the networking world that we call polarization, where traffic gets polarized. Now, what would prevent polarization from happening? Polarization could be reduced by increasing the number of flows. The more flows you have going across the link, the less polarization you should have, because you're going to have different flows that have different characteristics. Now, if I do a clear counters, and then I do a no IP Ceph, and I do the same ping, you can see that now EIGRP is going to be responsible for performing the load sharing. So ping 172.16.96.1, repeat 1,000, size 1,500. Okay. Let that go. And then if I now run my command to verify, show history, and it's not in there, I lost it. All right. Show interface serial 2.1, include count. Traffic. Can't remember which one it was. Let's just do the whole thing. All right. This output rate. So you can see, I didn't do it. Yeah, right here. 487 input. No, that should be 488 packets output, right? And if I do a show interface serial 2.0, pipe include packets output, you can see that 596 packets went over this link. Remember, the 2.0 link is better, right? It has more bandwidth, so it actually should have more packets than the serial 2.1. But you can see that EIGRP is now responsible for performing that load balancing. And it's pretty much equally distributed, relatively equally distributed. Remember, I cleared the counters before I did that second ping. So this is representative of those packets that I generated. Let's see, 596 plus 488, 1,084. There's some other packets that are being generated, obviously, because we're running routing protocols and stuff like that. But you can see where if we don't have Cisco Express forwarding enabled, that we rely on the routing protocol to do the load balancing or load sharing, whereas if we have Ceph enabled, then it's going to be some sort of per flow algorithm that's going to perform the load balancing. So just something to keep in mind when you're configuring load balancing. And if you start to recognize that maybe you're not getting equal cost load balancing, it is potentially because of Ceph, all right? Now, if I look at the routing table on HQ, which we already did, but we'll do it again, we can see that both routes are inserted into the routing table, but we can tell that we're running unequal cost multipath routing because the metrics are different, all right? But this is what it looks like when multiple routes get inserted into the routing table based on a specific destination. Do we have a problem here, though? Is there a specific problem that we're dealing with? Yes. Any idea what that problem is? We didn't do the same configuration on the other side. So what's happening on the other side of the link? It's only using serial 2.0. So we have asymmetric routing. Some of the packets are going to go over 2.1, but they're going to come back over 2.0. All right, that could be an issue if we have some sort of security implemented, or maybe we're doing some sort of analysis on flow information or whatever it might be. So we want to make sure that if we do apply variance on one side of the link, that we apply the same variance concept on the other side of the link, so that we do have symmetric routing and we have a symmetric configuration. All right. I'm sure they'll have us do that as part of the process, but so we can see both for IPv6 and IPv4 that we're doing unequal cost multipath routing. Show IPv6 route, and for the 96 network, we can see that we have two entries right, where's my 96? I'm missing it right here, okay? We have both entries, serial 2.0 and serial 2.1. Now notice here for the v6 output, it only gives us the metric for the best path. If I wanted to see the details for both paths, I would have to, not the 96, but I'd have to look at the route specifically. So I'd have to say show IPv6 route and then put in the route. And then I can see both paths. But it still actually doesn't show us which path is better. It's basically just giving us the metric of the best path. All right, but they do fall within the variance. All right, the second path falls within the variance. Okay, if I do a show IP protocols, I can also see that variance is applied right here. The maximum metric variance is 2. It doesn't really give us the specifics, right, what it's based on, because again, variance applies to the global EIGRP rib, not just specific peers or specific neighbors. It's something that was configured under the topology base, which is topology 0. So it's going to apply to any route that shows up under topology 0. Topology 0 is like if you're running VRFs, virtual routing and forwarding, you can have your base topology, but that you can also have custom topologies that you build, like VRF blue and VRF green, or VRF customer A or VRF customer B. And then you would have topology, different topology bases or topologies for those individual VRFs. All right? Same thing with show IPv6 protocols. I'm not going to run the command because it gives us basically the same output. The variance of 2 is applied, and that's about it. That's all you're going to see. Now, maximum paths is important, right? You see the maximum paths of 16 here, and then on our HQ router, we see a maximum paths of 4. So again, these will kind of work together. If my variance is fairly large, which means that maybe more than 4 paths could possibly be used, only 4 paths in this case are going to be used because we've applied a maximum path of 4. Make sense? So that maximum path is going to be the cap or the limit on how many paths can actually be inserted into the global rib based on the calculation of variance. Any questions about the unequal cost multipath routing? All right, so the next task that we have is we're going to set up authentication between BR1 and HQ. We're going to configure a keychain named EIGRP keys. Now, the keychain name does not have to match between the routers. The key string and the key ID has to match for each of the individual keys that get applied to the keychain, but the keychain name is locally significant. It is case sensitive though, so when you're referencing the keychain, you need to make sure that you put the appropriate case. We're going to have a key string of CCMP, which does have to match, and the key ID is critical. The key ID and the key string have to match. All right, so let's go to BR1. We're going to set up a keychain of EIGRP keys. And actually, I'm going to start doing a capture on this link as well, because I want to show you what the authenticated packets look like, as well as the unauthenticated packets. Get the capture running here. So let's go into our bench router and start to apply our configuration. Now you could actually use your scripting tool here to apply the configuration, because it's going to be identical on both sides. If you guys want to do that, you can. I'm going to do it individually. So we're going to create key number 1. Notice you have the option of creating quite a few keys. Only a little, only a small number of keys can you create. But we're going to create key ID number 1, and we're going to say the key string is CCMP. Now there's a bunch of other things that we can apply to the key itself. I can identify when the key can be used to accept packets. I can identify when the key can be used to send packets. That's something that we'll do a little bit later on. If you don't specify an accept or send lifetime, then the key is basically just considered valid infinitely, right? It's valid as soon as it's configured, and the lifetime is forever, and it can be used for sending and receiving. All right, so we're going to do the same thing on HQ. Config T. I'm going to be a little bit lazy here and copy this right here. Key 1, key 1, key string, CCMP. Okay? All right. Now, at this point, all we've done is created a key on our keychain. We haven't applied the keychain, but we can use the show keychain command to verify that the keys are actually valid. This is very important. When we do a show keychain, we want to make sure that the keys are valid. Also, spaces are allowed in the key string. So make sure that you don't put a space, like oftentimes people are kind of used to hitting the space bar after typing some text. If you put a space bar, you can have a leading space, but you can have a trailing space. If you put a space bar at the end of CCMP, it would be included as part of the key string. All right? So the keychain is valid there. Notice that the lifetime the key is valid. And same thing here. It's valid now. It's always valid because we didn't specify a sender or receive lifetime. And make sure that the key, if I did key string in this case, key string CCMP space, and then I did a show keychain, you can see the actual space because the quotes are spaced out away from the P and the CCMP. So that demonstrates that the space is allowed in the key string. All right, so make sure that that space is not there. All right, leading space wouldn't be accepted, but any kind of trailing spaces would be accepted. I just see that a lot where somebody makes that mistake and then authentication doesn't work. And if you're not looking specifically for that, you could very easily miss it, obviously, if you're just kind of, oh, there's the key string CCMP. All right? So now we've got our keychain created. The next thing is to go ahead and enable authentication for the peers. All right. Now notice they're doing this under the physical interface. That's because on BR1, we're running classic mode. We're not running named mode, which means that authentication is applied to the interface. Make sure you guys use interface Ethernet 1.0. So we're going to go into our branch router here, and I'm going to apply the configuration. That syntax does not look correct, but maybe it is. I thought the AS came after the mode, but let's go to interface Ethernet 1.0. Nope, it's correct, EIGRP 10. But notice here, in this particular case, MD5 is the only option that we have for this particular iOS. All right, so we're going to go ahead and apply MD5 authentication. Notice that the adjacency went down immediately because we haven't applied it to the other side. We're going to do the same thing for IPv6. And that's it. We've created the keychain. We're not referencing the keychain at this point. So I'm curious, what kind of key string is being used in this particular case? Because we haven't referenced the keychain. Well, actually, we're kind of in a no man's land right now. We're basically halfway through the config, which means it's not going to work no matter what, because we haven't tied in the keychain to the authentication process. That's why I typically would go ahead and put in the reference to the keychain first, and then I would enable the authentication. If I go to HQ, go under Router EIGRP Cisco, and go into the address families, we're going to apply this to interface 1.1, in our case, 1.1, and we'll apply the same configuration. Address family, IPv4, autonomous system number 10, and actually the syntax is identical, right? The only difference here is we're not referencing the autonomous system number because we're already in autonomous system 10 based on the address family mode of configuration. So we want to go into AF interface Ethernet 1.1, and we're going to say authentication mode MD5. And we'll go into address family exit, address family exit, address family IPv6, autonomous system number 20, AF interface Ethernet 1.1, authentication mode MD5. Notice here for IPv6, we do have the option of running SHA-256 as well. We didn't have that option for IPv4, but in this particular iOS, we do have an option to run SHA-256, which would be preferred, but we're going to go ahead and run MD5 in this particular case. All right. Again, we still don't have a peer. Notice that our peering relationship didn't change. It still says that the peer is down. All right. All right. So the neighbor's still down, but that's because we haven't applied the key to the authentication process. In OSPF, if you don't specify a key, there's a default key, but with EIGRP there isn't. So we need to make sure that we identify the keychain that's going to be used for the authentication process. Again, this is going to be interface Ethernet 1.0 on BR1, which you should already be in. All right. So I've applied that both to IPv4 and IPv6. Notice the adjacency still didn't come up because, again, we haven't applied it under our address family configuration on HQ. And to do that, it's very simple. It's the same basic concept, same command. We just reference the key. We don't have to specify, again, the autonomous system number because we've already gone into the address family, which includes the autonomous system number. All right, so exit here, address family IPv4, autonomous system number 10, AF interface, Ethernet 1.1, and we'll apply authentication there. All right, notice that the adjacency came up as soon as we applied the keychain. All right. I should also have my EIG. I didn't see the message for the IPv6 neighbor, so let's just make sure we have it. We do not have a v6 neighbor yet. Not sure why. I didn't see the message indicating that the neighbor was up. Let me do a show run section router and make sure I didn't mistype something. Let's see, so authentication mode MD5, authentication keychain EIGRP keys, AF interface 1.1, that's correct. So let me check BR1. IPv6 authentication mode EIGRP 20, MD5. IPv6 authentication keychain EIGRP. There we go. That's going to be the problem. That's because I did the cut and paste and I didn't pay attention. I referenced the wrong AS in my v6 command here. I need to reference AS20 and then that adjacency will come back up. All right. So pretty straightforward configuration. We could, of course, extend this configuration by creating multiple keys and specifying key lifetimes and whatnot. But let's take a look at what the packets look like at this point, right? So we're coming from 255.1. I believe that's the subnet, 255.1, yep. And if you look at, this is just a basic hello packet, but look at, there's now an authentication MD5 section. We see the authentication type 2, MD5. We see the digest, and we see the key ID. So when the other router receives this packet, it's going to say, oh, okay, I need to authenticate this packet using my key ID 1, because you use key ID 1 to create the hash. I'm going to use key ID 1 to verify the hash. All right? So the key ID and the key string have to match when you're configuring that information. All right? And then this is the hash that's generated based on that. So we never send the key string in the message. We always send the hash and the key ID. Another way, of course, to verify whether or not it's working is to simply verify your neighbors. But I do want to mention one other thing here, or show you one other thing. If you look at all of these messages, here's a reply. Let me actually grab a update. Here's an update. I'm not sure if this was before or after we applied authentication. Let's see. Hello, hello, hello. Let's do this. Let's apply a filter, selected, and we'll change it to a 2, a 3, a 4, a 1. Okay, this will work. All right. So if I go to the bottom here, I should see inside, inside of the packet. Because remember, this is what I wanted to show you. The authentication is part of the header. Every single EIGRP packet, remember the header used to stop at AS, and then we had our payload information. Authentication has now been added to the header. So every single EIGRP packet header is going to include the authentication information, whether it's a hello, a query, an update. We didn't see any queries or replies. Those were 4 and 5, or I mean 3 and 4. So 2, I can't recall what 2 was. Hello is 5, acknowledgement is 5. A update is 4. or 1, excuse me. Update is 1. So I think a query is 2 and a reply is 3, but whatever. Either one is going to, all of those packet types are going to include the authentication values. So you could, I'm not going to run these commands, but you could, of course, verify that authentication is working by verifying whether or not you have a neighbor. In your case, you would be running show IP EIGRP neighbors Ethernet 1.1, and that would indicate that you have a neighbor. All right, we can also identify, if we use the detailed option, I believe, if I'm correct, show IP EIGRP neighbor Ethernet 1.1 detail. It doesn't, I have to just do the detail. If it specifies whether or not authentication is configured on that peer, I believe I'd have to run the command show IP EIGRP interface detail to see that authentication is running on a particular interface. So this is Ethernet 1.1, yeah, and we see the authentication mode here. So show IP EIGRP interface detail will also tell you whether or not authentication is applied to a specific interface. All right? But if I have a neighbor, authentication must be working, right? Because then I wouldn't, the hello packets, if authentication wasn't configured correctly, the hello packets would fail because they couldn't be authenticated. And EIGRP verifies every single packet it receives against the authentication algorithm. So task 3, we're going to enable time-based authentication for BR2 and HQ. Now it's important actually that we don't use these timestamps because obviously we have to do a show clock to see what our current time is. I'm not actually going to configure this. You guys can go ahead and configure this if you'd like, but I will discuss it and explain it because I want you to understand how we're generating this traffic, right? So on BR2, they created a keychain called lifetime keys. And notice they've created 2 different keys in the keychain. Key string for this key is first key. The key string for this key is second key. Accept lifetime identifies whether or not the key is valid for receiving EIGRP packets. Send lifetime tells me whether or not the key is valid for sending EIGRP packets. Now, I will say this. You could get very, very specific. You could say, okay, for the first key, I'm going to use it on BR2 as my sending key. The second key is going to be my receiving key on BR2 and vice versa. Honestly, I wouldn't say that that's probably a good approach because it's going to make your authentication very, very complex. And what's also extremely important if we're using time-based keys? The time, right? Which means the routers have to have synchronized time. So you want to use something like NTP or some sort of time source to synchronize the clocks. Now, what we would typically do in this case is I would establish my first key and I would say, okay, that first key is going to be valid for the month of January, right, in 2020. And I would make the send and accept lifetimes the same. It's going to start on January 1st at midnight on 2020, and it's going to go all the way up to January 31st at midnight 2020. The second key, I would say, okay, this is my key for February. But I wouldn't start this key on February 1st, I would probably start this key on January 30th. Or at least have some overlap. Maybe it's not a whole day, maybe it's a 12-hour overlap or something like that. Because if the clocks aren't synchronized, if they're off by a little bit, even a minute, if you've got exact times, then your routing protocol might break. What happens if 2 keys are valid at the same time? The first key in the list is what's going to be used. So if key 1 and key 2 happen to be valid at the same time, I said I wasn't going to configure it. I guess I'm going to go ahead and do that because what I'm going to do is make my keys valid. I'm going to make both my keys valid. So let's go to BR2 in this case. I'm going to stop this capture because I'm going to do a capture on the other line here. Oops. And we'll go ahead and create that keychain here. And let's do key 1, key string, first key. Do show clock. And I'm going to say send lifetime. And notice I can specify the time to start. I'm just going to say 000000 on June 20th, 2020. And then lifetime is infinite. Okay, I'm going to say accept lifetime, and I'm going to do basically the same thing. All right, now normally if I'm going to create a keychain with multiple keys, I would have specific time periods where the keys are valid. But in this case, I'm only really just demonstrating that which key would be used based on the fact that the keys are valid, both keys are valid. So key string, second key, and I'm going to do the exact same send and accept lifetimes. And then I'm going to get really lazy. I'm going to say do show run pipe section key. And I'm going to just take this and copy it. And I'm going to paste it into HQ. All right. So I know I have an identical configuration now. The keychains and key strings and lifetimes are going to match. If I do a show keychain, the command to create the keychain has a dash in it, or the command to create the keychain doesn't have a dash, so I shouldn't use a dash there. But we can see that the keys are valid now. All right, we have two keys that are valid, first key and second key. Now again, all I have to do is apply this to the configuration. Router EIGRP Cisco, router EIGRP Cisco, and address family IPv4, autonomous system number 10, AF interface, Ethernet. I believe it's one on this router, 1.2, and I can say authentication, mode, MD5, authentication keychain. Here it has a dash. It doesn't have a dash there. And then I can specify the name of the keychain, which is right here, EIGRP lifetime keys. All right. And then I'm going to also do that same thing for address family IPv6, autonomous system number 20, AF interface, Ethernet 1.2. Yep. Authentication mode, MD5. Authentication keychain, EIGRP. So go to BR2. I'm going to apply the same configuration on Ethernet 1.0 for BR2. Interface Ethernet 1.0, authentication, IP authentication, mode EIGRP 10, MD5, IP authentication, keychain, EIGRP 10, and grab the name here. And IP authentication, sorry, IPv6 authentication mode EIGRP 20 MD5 and IPv6 authentication keychain EIGRP 20 EIGRP lifetime keys. And you'll see my adjacencies will come back up. Both my V4 and my V6 adjacencies came back up. But here's the thing. I've got two different keys that could be used. I have two keys that could be used because they're both valid. But if I do my Wireshark capture, let's close this out. And I do my Wireshark capture on the link, you'll see that I'm using key ID 1 because it just happens to be the first valid key in the list. We always search the key string or the key chain from the top down, which is why you could use one key for sending and one key for receiving, because if the lifetime for sending is not valid for key 1, but the lifetime for sending is valid for key 2, then we would simply use key 2 to send traffic, and the vice versa. On the other side, we would see the same thing. So here we can see that the key ID being used for the authentication is key 1. All right? Now, if I made that key invalid, let's say I went to HQ, do show run pipe section key, and I went into my keychain, and I went to key 1, and I said send lifetime 000000 June 28th, 2020 infinite, do show key chain, you can see that it says valid now. It should have changed it. Still got the, oh here, send lifetime. Notice it doesn't say valid, right? So actually, when HQ is now sending EIGRP packets, it's sending it with key number 2. So HQ in this case is going to be the 255.5. So if I go to my Wireshark capture and I grab 255.5, I should see that I'm using key number 2 in this case. It's still working, by the way, because the receiving router's key 2 is valid. See what I'm saying? The accept lifetime on BR2 for key 2 is valid. If I was to make it not valid, then obviously the adjacency would fail. I'll show you. So if I go to BR2, do show run section key, and I go into my keychain and go to key 2, and I say the accept lifetime 000000 June 28th, infinite, oops, 2020 infinite, we will lose our adjacency, right? The adjacency went down because the router on the left is sending hello packets with key 2, and key 2 is no longer valid for accepting packets on BR2. Show key chain. I can see that the accept lifetime for key 2 is configured, but it's not presently valid. Does that make sense? So you can get pretty creative with these keychains, and you can specify, you know, kind of overlapping keys, one key for sending, one key for receiving, and then they can you can rotate through them every 30 days or whatever. Or what, I mean, depending on how many keys you want to put in the keychain, you could rotate every week, right? If you want to put, what, 52 keychains or 52 keys in your keychain, that would probably drive you crazy, but yeah, you could do that. All right. So time-based authentication is useful, and it is something that we actually use. But again, it's critical to understand that if you're going to do time-based authentication, you need to make sure that the times are accurate. Because if the clock on the router is not correct, the key is not going to be valid. All right? We already did the show keychain to see that the keys in this particular case It would have worked. The syntax they had here would have worked because we made the keys infinite. We didn't actually specify. Actually, they did specify an expiration date. So this keys would not have worked in our particular case, because they would have already expired April 8th of 2019. And because we're using GNS3, the routers are taking their time from the PC. So whatever the PC's time is. All right. All right. I think you guys get the general idea. Here they're applying the keychains. I already did all this. I kind of just jumped through and did it. But here they're applying the keychains to the OS or the EIGRP process on Ethernet 1.0 and Ethernet 1.2 here. Same configuration. It's no different. The only difference is we're using time-based keys as opposed to infinite keys. Again, to verify the keys, you can do a show IP EIGRP interface detail to see what keys are applied, what key chains are applied. But if you have neighbors, you know that authentication is working because there's no way to have a neighbor if authentication is not working. All right. They did the show EIGRP address family interface detail. Same command that I showed you guys. They used a grep command. It seems like it would be easier just to say show EIGRP interface detail and look for it because that's a long command. But you get the idea. They're using the interface detail command to see that authentication has been applied, and we're using keychain EIGRP underscore keys. All right. So our last step in this case, and I don't believe it's going to work for v4. We'll give it a shot. Actually, with address family mode, it should, but they want us to enable SHA-256 authentication, which is recommended, right? MD5 is a 128-bit hashing algorithm, and it's certainly not going to be as secure as SHA, the 256-bit hashing algorithm. So we're still going to use authentication, but in this case, notice that they're not referencing a keychain. This is another way you can configure authentication. You don't have to use a keychain. You can actually attach the key directly to the authentication command. All right, so if I go to my distribution router, let's grab the distribution router here. Okay, config T, router EIGRP Cisco, address family IPv4, autonomous system number 10, AF interface, and in this case we're applying it to our serial interfaces. 2.0 and 2.1. Interface serial 2.0, and I'm just going to copy the command here. Authentication mode. And notice we have HMAC SHA-256. That wasn't available in classic mode, by the way. Classic mode, we didn't have SHA-256 available for EIGRP. We had it available for IPv6, but not IPv4. And then the secret key secret underscore key was the key string. We're going to do this on AF interface serial 2.1 as well. Okay, which means we're going to lose our adjacency. Again, during the process of configuration, you'll lose the adjacency. We'll do this on address family IPv6 as well. Autonomous system number 20, AF interface serial 2.0. Oops. And authentication secret key, AF interface serial 2.1. All right. Go to the HQ router and basically do the same config. You can do this as well, show run pipe section router. And you could, it might be a little bit more challenging. You could at least copy, well, not really, because you don't want the summary address on. I was going to say you could copy and paste on the HQ side, but you're not really going to be able to do that. So unless you just did it in Notepad. address family IPv4, autonomous system number 10, AF interface serial 20, authentication, SHA, authentication mode, SHA, authentication mode, HMAC, SHA 256, secret key, and exit, oops, dang it, I forgot to do it on the other interface, serial 21, exit, address family IPv6, autonomous system number 20, interface serial 20, and 21, and done. So our adjacencies come back up, and we're good to go. All right. Now, as far as what we see on the Wireshark capture, the only difference is the mode of authentication. Everything else looks exactly the same. So if I come back to GNS3 here, and I just do a capture on my serial link, I'll see that authentication running across the serial link as well. I went through that relatively quickly because it's really just a repeat, right? We're just repeating the configuration. So if you guys get through page 120, you'll be basically where I'm at. All right. And again, if I go back in here and verify any one of these messages, you'll see authentication. Again, just below autonomous system, because it's part of the packet header, authentication type is type 3. Which is SHA 256, and notice the digest is much larger in this case. It's a 256-bit digest, so it's pretty significant. Overall, the general concept of authentication is identical. We're not doing any kind of different authentication in this case. All right. We verify our neighbors. Again, if we have neighbors, then authentication must be working. We can still do a show IPv6 interface detail, and we can see authentication mode. In this case, we set the key directly on the authentication line. So we're not using a keychain. We're actually using the secret key that's established in the authentication configuration. Also, if you have your routes, routing doesn't directly relate to authentication, but if you have routes, then you must have authentication, because you're not going to get a neighbor without authentication, which means you're not going to get routes without authentication. So they just go through and they verify the routes on each router. Okay? All right, that ends that particular discovery. We'll see you guys in the next discovery.